Hey guys, welcome back. We're going to talk about what a free response question would look like. Okay, so a couple of these, I think I said in class, I'm going to find a free response question that you'd have to make a two-way table, or if you like making Venn diagrams, right? And those have the same four numbers in it, 1, 2, 3, 4, 1, 2, 3, 4, right? Or that you would have to make a tree diagram for. Now notice we had a couple of those in the multiple choice. So I could easily just make those multiple choice questions and then just eliminate the choices. So there'll be two questions, one where it'll probably easy to answer if you make a two-way table, and another would be designed to answer with a tree diagram. But let's dig into some other examples that the book gives us. Okay, so the book actually gave us 4. I've kind of hidden this question number 14 because I didn't want to use it. So let's take a look at question number 11. It says a two-way table summarizes the data where the students of a certain high school eat regularly in the cafeteria. If you choose a student at random from the table, so that means if the denominator is 805, what is the probability that the student eats regularly in the cafeteria and is not a 10th grader? So that was this one, eats regularly in the cafeteria and is not a 10th grader. That's all these people. Okay, so I'm not going to finish out the question. Go ahead and add those up and put it over 805. I'm actually tempted to even finish the question because a lot of people watch this video without the sound on. 130 plus 122. 130 plus 1. Oh boy, here we go. Here's an add. 130 plus 122 is 252 plus 68. So 320. And we get next question. If you chose a student at random who eats regularly in the cafeteria, so that means my denominator is something different. I'm choosing a student who eats regularly in the cafeteria. So these people are completely ignored. And I'm picking from the 495 students. What is the probability that one of these students is a 10th grader? So we get, so what does that look like? What's the probability that they're a 10th grader given that they eat in the cafeteria? Okay? C, are the events 10th grader and eats regularly in the cafeteria independent? Okay, so the probability of a 10th grader, is that equal to the probability of 10th grader given you eat in the cafeteria? And is that also equal to the probability of 10th grader given do you not equal in the cafeteria? Now notice we already answered almost exactly all these questions in the multiple choice section. So it's kind of redundant for me to give this question in a free response question. And I didn't have to make a Venn diagram or a two-way table. So you're going to likely not get a question just like this, but this is good practice for the multiple choice. Okay, so what's the probability that you are a 10th grader? Well, it looks like that's 209 out of 805, right? What's the probability you're a 10th grader given that you eat in the cafeteria? We already figured that out. Right? Then what's the probability you're a 10th grader given you do not eat? So there are 310 people that do not eat in the cafeteria, and of those people, 34 of them were 10th graders. So let's figure out what each of these decimals are and if in fact they are the same number. 209 over 805. 0.2596. 0.2596. I already have not equal to 34 divided by 310. 0.1097. 0.1097. Nope, not equal. So are these independent? Justify my answer. Look at all this justification. This is a common question, and I think every year it's always ended up on a test at some point, either the midterm or I noticed it ended up on the exam. So we notice here that they are not 10th grader and eating in the cafe are not independent because those items are not equal to each other. Because those are different. These are different probabilities. All right. Question number 12, it says, 3 machines, A, B, and C, are used to produce a large quantity of identical parts at a factory. Machine A produces 60% of the parts. Machine B produces, while machine B and C produces 30 and 10. Historically, records indicate that 10% of the parts produced by machine A, so you're the defective or you're not defective. Historically, it indicates that 10% of the parts produced by A, so that means this is saying 10% of 60. So that would be 6, right? 10% of 60. 10% of the parts produced by machine A are defective. That leaves 54 of them that are not defective, compared with 30%. So what's 30% of 30? That would be 9, right? Leaving 21 not defective. And then 40% of machine C are defective. So what is 40% of 10? That'd be 4. There you go. So not very many of them are defective. 19 are defective out of a total of 100, leaving us 81 that are not defective. Suppose we randomly selected a part produced at the factory. Find the probability that the part is defective. We got, right, 19 out of 100, or 0.19. If the part is inspected and found to be defective, so if the part is inspected and found to be defective, so it is one of these 19 to begin with, what is the probability out of these 19 that it was produced by B? Well, 9 of those 19 are produced by B. So that's equal to 0.747. This was what we designated student of the week, where you were able to kind of parse this out and get this Democrat, Republican, continental United States thing right. This is the question that will be on the test, and the numbers will just be changed. Now, can you use a two-way table? I totally did. If you look in the back of the book, they actually use a tree diagram. You can use either one. It doesn't matter to me. The book demonstrates one. I just demonstrated another. Use whichever one you're most comfortable with. Okay. Question number 13. A Dicey Dave diner, the dinner buffet usually costs $12.99. Once a month, Dave sponsors A lucky buffet night. On that night, each patron can either pay the usual price or roll 2 fair 6-sided dice and pay a number of dollars equal to the product of the number showing on the 2 faces. The table shows the sample space. Okay, so as we look here, we're like, ooh, if I end up rolling a 1 and a 1, then it sounds like maybe I only pay $1 for this. So again, let's read it again just to make sure we understand the rules of the game. At Dicey Dave's Diner, the dinner buffet, that's the typical price. Once a month, Dave calls it the Lucky Buffet Night. On that night, each patron can pay the usual price, or, so you can pay the $12, or you can roll the 2 fair 6-sided dice and pay the number of dollars equal to the product. Okay, so if I roll a 1 and a 1, then 1 times 1 is 1, and I only paid $1 instead of paying the $12.99 that I would normally pay if I came on a night where they didn't have the deal. Okay. Now they made the table for you, which is nice. We could have made it. And again, it makes sense. This is 6 times 6. This is 1 times 1, and every other combination of the product. Okay, so question A says, a customer decides to pay Dave's to play the game. Find the probability that the customer will pay less. So this reminds us of who will win the last banana. These customers would pay less. Yep. Okay, those customers would pay less. Find the probability that the customer would pay less. Okay. So the probability that the cost is less than $12.99 is equal to, and we'll count these up, 6, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. 23 out of a total of 36 outcomes. So A is 0.639. Okay. So you're like, oh, I have a pretty good chance of paying less, so maybe I should play the game. A group of 4 friends, ooh, this is like the example we did in class, isn't it? A group of 4 friends comes to Dicey Dave's to play the Lucky Buffet. Find the probability that all 4 of these friends end up paying less than usual. So that's the probability. This would be one person paying less. This would be this next person paying less. This would be the third person paying less. This would be the fourth person paying less. So the probability that all 4 people end up paying less would be the same thing as this to the 4th power. When we type that into our calculator, we get 0.167. What does this tell us? Well, even though we are likely to pay less, we're not likely that everyone in the group pays less, because that's a pretty low probability. So someone's going to have to pay more. And is that going to be cool? How's that person going to feel? Right? All right, next question says, find the probability that at least one friend ends up paying more. Okay, that's too difficult. That would take too much time, because that would be the probability. If this is the probability that you pay less, then the probability you pay more is its complement. So what would that be? That would be 13 over 36. So it says, what's the probability at least one pays more? Okay, that could be the first person pays more, or the second person pays more, or the third, or the fourth, or maybe the first and the second pay more, or maybe the second and the third pay more, right? It's too many possible outcomes to add up. So we want to say that the probability of at least one pays more is equal to the one minus the probability of no one pays more. And so what would that be? Well, the probability that no one pays more would be this answer here. This was every single person getting less than the $12.99. So this is the answer when no one pays more. So what's the chances at least one pays more? 1 minus this number. All right, that would be 0.833. So there's actually a really good chance that at least one person, could be more, could be 2, could be 3, could be 4 people pay more. There's a good chance at least one person pays more. This is a very difficult math problem. So I would think of this one, if it shows up on the test, as a bonus question. I can even give this question to math teachers that work at the school and they would struggle with this question. So don't be too frustrated with part C. You can still get a 5 on the exam if you don't get part C. But it's a great brain teaser. Thanks, guys. Good luck.